So this is the second video for Power Engineering module EE114, and we will be talking about power in a single phase AC circuit now. So the standard formula P equal to VI is still valid in a single phase AC circuit, and the average power can be calculated. So you basically have to integrate this over a single time period, and then you have to divide it by the time period. So you will get Vm Im cos phi over 2. So what are these terms? So Vm and Im are the amplitudes of the voltage and current sinusoids. The cos phi is cosine of the phi thing. So what is phi? Phi is the angle by which the voltage phasor leads the current phasor. Leads means by the angle by which the voltage phasor is ahead of the current phasor. Right, so it is basically phi of V minus phi of I. Now we will start talking about RMS quantities now, because this too is going to get a bit frustrating. So what we will do is that we will take the RMS of the voltage and the current. So how do you take RMS? This is the common formula. No, you integrate the square of the function over a time period. You divide by the time period, you take the square root. So for a sinusoid, it is Vm over root 2 if it is voltage. So voltage will take a root 2, current will take a root 2. This 2 will go away. You will get PAV is equal to VRMS IRMS cos phi. That's it, right? And this is why most phasor diagrams are drawn with RMS quantities that I had mentioned previously. And from now on, all phasor quantities that I mentioned will be RMS. So when I am actually talking about V, I will actually be meaning Vm over root 2 when I'm not adding the tilde over the head. So we have calculated the average power. But power does oscillate because it's the product of two sinusoids. So it has this oscillating component with it, which we must accommodate. So how to represent that? Well, that oscillating component, if you find out, it will be VRMS IRMS sine phi, and it will oscillate at double the frequency of the voltage and the current. So as you can see, I've taken VRMS and IRMS, so actually it must have been VM IM over 2, and we are dealing with RMS quantities, so that made my life a little easier. Now this oscillating component is actually a good measure for the power that is dissipated in the transmission lines, which we have been talking about is lower in AC than in DC, and this is why it allows you to actually minimize this power loss in the transmission lines. How does it do it? Let's see. So suppose that we have some load. So the characteristic of most loads is that it will draw some given rated power at some given rated voltage, but the current through it is not constant. You can vary it. But since you have to keep the power constant, you have to keep VI cos phi constant, because this is the actual average power that you will be going to be giving to the appliance. So VI cos phi must be kept constant, V must be kept constant. So I cos phi will basically be constant. Now see, as phi increases, we know that cos phi will decrease, and as cos phi starts to decrease, to keep this whole thing constant, I will start increasing. So you can see that as phi increases, I increases, and I square R is the loss in the transmission line, if R is the resistance of the transmission line. So basically what we are dealing with is that we have to minimize phi, and instead of phi we start talking about minimizing sine phi. And if we minimize sine phi, that is same as saying we are minimizing q. So basically what we are doing is we make a mathematical framework to reduce this q component, which will be called the reactive power. Once again, why do we need to do this? Because we need to minimize the power loss in the transmission line, which is proportional to I square, and the I square loss increases with phi. So we need to reduce phi, which is same as saying we need to reduce q. Now for doing this, the mathematical framework we build first comes along with a new power, which is called apparent power. We define it as VRMS IRMS. Now remember that Q was basically VRMS IRMS sin phi, P was VRMS IRMS cos phi. And so get this very nice identity that P square plus Q square is S square. And as soon as you notice that, well, P square plus Q square is S square, and P had a cos phi component, Q had a sin phi component, it brings into your mind a hypotenuse triangle where the hypotenuse must be S and the sides must be P and Q. It looks like a Pythagoras theorem. So this motivates one to forcibly create a phasor out of S, which means S is not technically a phasor. It is not a pure sinusoid because it has an average component that is not zero. But if we try to forcibly create a phasor out of S, it would look something like this, where P and Q are the sides and S is this whole hypotenuse. This theta, which is also phi, will be the angle by which the voltage phasor leads the current phasor, right? So we make this q point along the imaginary axis, we make this p point along the real axis, and then this whole thing will be called complex power. So S, instead of being just an amplitude, now also has a direction. So that's why, making it a complex number, we have put a tilde over its head. And this diagram with P, Q, and S pointing up is called a power triangle. Remember, our ulterior motive is to reduce Q, and we will come back to that in the last slide. Just remember that. Keep this theta in mind, or phi, whatever you want to call it. It's also going to come up again. So we go back to impedance, because we had said that it is actually a very complicated, complex number. So how is it hiding any secrets, right? So first, reanalyze impedance. So this is what impedance looked like. The resistance was along the real axis, the reactance was along the imaginary axis, and we had the impedance. We had this angle. Right. Now, complex multiplication adds angles, right? If you multiply two complex numbers, then the phases will get added, right? So that means that since v is equal to zi, this phi angle will come here, and if you add it with the phase of the current phasor, you should get the phase of the voltage phasor. But we define the difference of the voltage phasor and the current phasor to be the angle of the power triangle, which means these two angles are actually equal. The theta we had mentioned before and the phi that is coming right now, they are actually equal. And this is actually interesting because this is also a right angle triangle, that was also a right angle triangle, this angle is same as that angle. That means the analogy must be running much deeper, right? So actually, just look at these two triangles a little bit carefully. The angles are same. That means by, maybe AA similarity, you get two triangles to be similar. Now, if the two triangles are similar, that means the sides are in some ratio, right? Each of the sides is having the same scaling ratio. So what's that scaling ratio? So you can take any side and take its ratio, and we will get what that scaling ratio is. So let's just take this hypotenuse. So the length of this impedance is V over I. Remember, now we are talking about RMS quantities. We have not put tildes over their heads. So we are talking about the RMS values of the phasors. Similarly, S is Vi. So that means that S over Z must simply be I square. So the scaling factor is simply the square of the magnitude of the current phasor RMS. And observe that this means that the power triangle is simply a phased up impedance triangle. They are both similar. It's just like you have scaled it up. Now let's talk about a formula for S, because S was a complex quantity and it would help to have a formula for S in the terms of the voltage and the current phasors. So after many trial and error, you will see that the combination of VI conjugate works, where basically I conjugate is the complex conjugate of the current phasor I. And well, that works because the complex conjugate has the minus of the angle. So the angle of this is theta v minus theta I, and its amplitude is also correct. So yes, it works. Now, if you want to calculate the powers, just calculate the V and I phasors, multiply them while taking the conjugate of I, just remember that part, and then take the P and Q as the real and imaginary components, and you're done. We can confirm that since S is Vi star, where V is Zi, so this is Zii star, and Ii star means the square of the amplitude. You will once again get this current square scaling thing. And now we take a step back to observe complex conductance. So we had talked about complex resistance, so we should also talk about inverse of that, right? So we define a value called admittance, which is called 1 over impedance. And once again, since this is a complex quantity, we will try to break it into real and imaginary components. And hence we have an admittance triangle. So what are the two components? The real thing, as usual, is always the same, so it's still the conductance. The imaginary component is called the susceptance, and hence we can write Y as G plus JB, where the conductance are there and the susceptance is there. And this angle will reappear because you see, if you divide a complex number, if you take the multiplicative inverse, if you do 1 over Z, the phase of this new Y will simply be minus theta instead of theta, but that angle will still come again. And this angle is reappearing so many times that its cosine has its own name. It's called the power factor. And it is so called because it is the ratio of the real power that you can measure and the apparent power. So that's why it's called the factor of power, or power factor. And it's denoted as PF. And it cannot define theta completely because we are actually giving cos theta. And there is a plus minus sign ambiguity still remaining in whether the theta is positive or negative. To remove that ambiguity, you say that if theta is positive, we call the PF as lagging PF. If it is negative, we call it as a leading PF. So since sine theta was proportional to Q, we can sometimes say that if the reactor power is positive, we say that the power factor is lagging, and vice versa. So now we again return to our original aim in this whole thing that we have done, which was minimizing Q. And this is done something called power factor correction. This is how we minimize Q. So the process of minimizing reactive power that is going from the source, because that is what will come in the transmission line. That is what we want to minimize. But we have to maintain the power and voltage across the load constant. Now this thing is called power factor correction. Since you want to keep the voltage constant and the power constant, you cannot add anything in series because the source is also giving the power and voltage at the constant terminal voltage. But you can add something in parallel. So this is a phasor diagram that most people use for phasor or power factor correction. So here we have three phasors: the actual current that is coming from the source, the load current, and the capacitor current. So what is this capacitor current? See, most loads are inductive in nature, right? So if the load is inductive in nature, it makes sense that you add some capacitor in parallel to try and compensate for that reactive power. The value of that capacitor should be such that the current flowing through that capacitor should match up, and it should completely pull this up so that theta 2 becomes 0. This can be calculated using the admittance triangle. Since two things are parallel, their admittance would simply be getting added. Now here's another warning, and that's to not forget the imaginariness of Q. Q is not real, Q is imaginary. It is called reactive power, and there is a reason we call P real power, because it is real. Q is not real, and it averages out to 0 in a single cycle. And keep this in mind because, see, inductor has a positive Q drop across it. It absorbs reactive power is what some people can say. And the reason for that is Q becomes positive if you have an inductor there. Because see, an inductor creates an impedance of j omega L, and hence its voltage phasor is leading its current phasor. So there sin phi is almost 1. So phi is positive there, and hence the Q for an inductor is positive. So an inductor is acting like a reactive power sink, and hence a capacitor must be acting like a reactive power source. But this does not mean that they are sources and sinks in real life. They are not actual powers, because Q is still imaginary. All they do is store and then release the power that they have stored. They don't dissipate or create any power. So over a cycle, C stores some power, then releases some power, L stores some power and releases that power. The way we have defined reactive power is such that it looks like C is giving the power and L is absorbing the power. And it averages out to 0 over a cycle. So that's what is happening. And understand that PF correction is also very well understood using this, because see, we added a capacitor in parallel. So you can see that the load needs two kinds of powers. One could say it needs a reactive power and it needs a real power. The source is providing the real power, and to make that power loss in the transmission line 0, we later add the reactive power by adding a local capacitor in parallel. Once again, Q is not real, it's an imaginary quantity. This is the end of the second video. Thank you.